Recorded is rolling. It is Thursday, January 23rd. All right, so in the past couple days, we have wrapped up rotational dynamics. Here's my top scientist list for rotational dynamics. This is for my honors classes, 4 honors classes. All right, so awesome job if you made the list. And then I also have a conceptual class. They have their own thing going on. They've got their own quiz. Okay, so a little bit different. So here's my conceptual students, top scientists. All right. Also have AP class, but I got a separate video for them today because slightly different thing what we're doing. All right, so there's top scientists. Awesome job. You made that list. All right, so we are moving on to a whole other set of topics. You guys got materials at your desk for a pendulum lab. That's what this is leading to. And you guys have all new thumbnail notes. So these spring thumbnail notes. So I give you guys in this plastic sleeve. There's a bunch of pages here. So these are all new. So this is for you guys. Of course, you guys keep this. Right. So there's your spring thumbnail notes right there. And then also on your desk is, well, this page that has, looks like 3 different lab tables. You guys see 3 different lab tables? Okay, there's a reason for that. Go to that. And then on the back side are, 4 sets of axes. So this is going to lead to 4 graphs. Now, I'll help you guys put these graphs together tomorrow based on the lab data that you're collecting today. Okay. If you have 5 or 10 spare minutes at the end of class, and you might, if you work really efficiently, you might have a little bit of time. See if you can put together some of these graphs. See if you can figure out what I'm looking for, what variable on which axis kind of thing. Right? So 4 graphs from 3 lab tables. I wonder what that looks like. Right. So here's big picture what we're doing. Set up pendulums. So I got a little pendulum rigged up right here. Okay, you guys see this? Here, guys, everybody focus up here. Everybody look here. You guys got phones away? Look up here. Think about this. Okay. So there's some laws of the universe that's governing how this is oscillating back and forth. Right? Oh, yeah. So for example, how much time does it take to go from my finger back to my finger? You guys see that? How much time is that? And what variables could that depend on? Okay. So see if you guys are following. What based on what I just said, say show of hands. What am I defining as the time period? Am I defining time period as from left to right? Or am I defining time period as left to the right, back to the left again? Okay. Guys, which one? Which one is time period? Is it the second thing I said? Yeah, from the left to the right, back to the left again. That's right. So however much time that is one full time period. You guys have stopwatches on your desk, okay? And what variables do you think could possibly affect how much time that takes? Okay. So I have one candidate as an independent variable. Maybe this mass here, or the weight. You could say, I know mass and weight are different things, but I mean, they're directly proportional, right? So it's got right. So okay, I got different lab masses lined up. Is what if I unhook the string here and hook it to these different lab weights? Okay? So as the lab mass or the lab weight increases, here I'm going to narrow this down to 3 basic hypotheses. Let's see, show hands. What do you guys think? As I increase the mass, increase the weight, is that going to also increase the time period? That's to say it would slow it down, right? Would it decrease the time period? Let's say it swings back and forth faster, right? Or would it have no effect at all? Maybe I change out these lab weights and it's the same time. It's like the same time over and over, right? So show hands. How many of you guys think if I increase the lab mass, it's going to also increase the time period and slow it down? Who says that? Who thinks as I increase the lab mass, it's going to decrease the time period, say speed it up? Who thinks as I increase the lab mass, it's same time over and over? Who thinks same time? Okay. So I think I'm seeing votes on every one of those hypotheses. So somebody's right. You guys will probably know by the end of today. Right. So there's one pair of variables, right? This mass versus this time period. Okay? What do you think is another potential independent variable you'd have to investigate? The length. This length right here. Okay. Speaking of the string, probably a good time to mention. Do you think that the mass of the string is tiny, tiny, tiny compared to this lab weight that's actually hooked onto it? Yeah, and you guys know in this class we do simplifications all the time. Sometimes we'll round gravity a little bit, or we're assume away friction or something. So, because for this pendulum, we are assuming that the string mass is negligible, right? Right. Because guys, if I replace the string with like an iron bar, do you think this would probably swing back and forth a little bit differently? Right. Right. So all right. So we're gonna say all the mass all the way same. All right. But the length. Okay. So now we're focused on the length of the string. Okay. So I can have a short pendulum versus a medium pendulum versus a long pendulum. As I make the string length longer, longer, longer. Let's say same basic 3 hypotheses. The longer the string, is that going to increase, decrease, or have no effect on the time period? How many think a longer pendulum is going to increase the time period, say swing back and forth more slowly? Okay. Who thinks that the longer pendulum is going to decrease the time period, make it swing back and forth more quickly? Okay. Who thinks that there's no relationship between those two? Right. Let's get a bit more granular because I saw the most votes on the first thing I said. A longer length pendulum is a longer time period. Most of you guys said that. Okay? If you said that, do you guys think if you double the length of the string, that would also double the time period, or less than double, or more than double? Right. Now I'll just let that question float around so you guys can think about that. Right. That's assuming that it increases at all. All right, so there's two potential independent variables. I could swap out this mass, I could swap out the string length. What's another potential independent variable? What do you think?
How far are you starting?
The starting angle from the vertical, this angular displacement, okay? Which you can measure with a protractor, right? There's a protractor, okay? All right, so let's say same three basic hypotheses. Right? As you increase this angle from the vertical, say 5, 10, 15 degrees, is that going to increase, decrease, or have no effect on the time period? How many of you guys think if you make this angle bigger, go from 5 to 10 degrees, it would take more time to swing back and forth? Who thinks that? More time. Who thinks as you increase this angle, that'd be less time to swing back and forth? Who thinks if you increase this angle, it had no relationship with the time period? All right, well, it's probably one of those categories, right?
I feel like it's the first one.
All right, so you got some votes there. All right. Now there is another potential independent variable that we're not going to investigate, and that's the gravity field. Okay. Here, we'll do some thought experiments here, guys. If I took this pendulum to the moon, now on the moon, is there a little bit of gravity? Yeah, a little bit, but it's really tiny, right? It's like 1/6 of Earth's gravity. So it's really, with this on the moon, swing back and forth like this, like, or swing back like, yeah, really slowly, right? So I'm going to call that some kind of inverse relationship between gravity field and time period. Like the more gravity, the less time period, and vice versa. All right. But can't really test for that in this class, so that'll show up in the textbook equation. But in this class, we'll focus on the proportional relationships where, well, we're going to be juggling these other 4 variables. Okay, guys, get that? All right. So with that big picture in mind, let's look at your guys's lab page. Okay. So go ahead, write your name. Guys, everybody write their name right here. So when you eventually turn this in, probably tomorrow, then you know who to give the points to. All right, Pendulum Lab. It's going to be Pendulum Lab. So you guys write your name. You guys write Pendulum Lab. You guys got all that? Name, Pendulum Lab.
Oh,
right.
Got it.
All right. And you guys have seen many of these lab tables throughout the year. So hope you guys have it. You got trial, and 1, 2, 3, 4, 5, 6, 7. You have some variable here and some unit corresponding to that variable. Right? What are you measuring in? Right. So I won't do this whole table with you guys, but I'll get you guys started with a little bit of it. Right. So you guys told me you could measure mass as a potential independent variable. And guys, what unit do you want to measure mass in?
Grams?
Grams or kilograms? I'll leave it up to you guys. You give me grams or kilograms is okay. I'll write kilograms because maybe that'd be safe if we want to make an exact equation, but grams is fine. Whether you measure grams or kilograms, you'll get the same proportion relationship by the time you get to the graphs. Right, so it doesn't matter which way you go. Right, grams or kilograms. Right. You guys said possibly the length. What do you want to measure length in? I heard centimeters is good. I'm going to write meters myself. Right.
Inches.
Well, let's tend to stick to a metric just for good practice. Even if you do inches, you'll still get the correct relationships at the end. So I guess that could be okay too. Right? But centimeters and meters a little bit better. Okay. And then you guys said the starting angle from the vertical. And what could you measure the starting angle in?
Degrees.
Degrees. Right. Actually, guys, the fact they just wrote degrees is sort of a big hint as to maybe how this is not going to play out. Right? Because guys, what's the other way to measure angle? Radians, right? And it's some, well, you guys know what this is all leading up to. It's leading to some master formula. The time period equals is going to be some formula here. It has something to do with this arrangement of variables. Okay. So if I'm measuring in degrees, that tells me if it pops up in the equation, it has to be inside a sine or a cosine. Okay. Or some trigonometry function. Okay. Because if it was not inside a trigonometry function, because if you were to somehow directly multiply or divide the angle, you would have to have measured in what unit? radians, right? Okay. The fact that I wrote degrees is maybe a big hint that it's not going to play out like that. Okay. Okay. Now that's not all the variables you need. You need some more columns for some more things you got to write. All right. Oh, speaking of time, maybe time could be your dependent variable, sort of. Right. Here's what else I meant to mention. You guys are using stopwatches, right? Is what's a better way to measure time? Should I go like this? Should I go start, stop? Should I do that? Or should I go like start, 1, 2, 3, 4, stop, and say, okay, now I time maybe multiple oscillations, 5 or 10 oscillations, and then divide so I can get divided out. Okay. Because what's the better way to measure time?
Better way to measure time?
The first thing I did, where you just tried to measure one, bam, bam, or the second way, where I count a bunch of oscillations and divide by the number of oscillations.
Second one.
The second thing I said. Okay. Why? Why is the second way better?
It's second average. There's more room for wiggle. There's more wiggle room.
Ah, yeah, because it's more accurate, right? I can divide out my error, right? Especially using the stopwatch, and you've definitely seen this throughout this class, is there can be a lot of error trying to figure out exactly when to start and stop it. And if this is like a fraction of a second to swing it back and forth, which some of these might be a fraction of a second, and if you're off by a half a second, then by the time you get to these graphs, they're not going to make any sense. They'll be all wonky all over the place and won't make any sense, right? Right. But if you do, like, for example, 10 oscillations and divide by 10, then that half-second error of starting and stopping the stopwatch also gets divided by 10, right? So then it's a lot more accurate. And then by the time we get to these graphs, there will be definitely some pattern that pops out. You're like, oh, either some kind of direct relationship or some kind of square root relationship or something. Okay. All right. And also, why do I have 4 graphs but only 3 lab tables? Maybe I'll let that question float around too. Of course, I'll help you guys put the graphs a little bit together tomorrow. Okay. But if you have a few spare minutes at the end of class, maybe you want to do a head start and start working on the graphs today. All right. I think I got you guys all set up. Go ahead, get all your data today. You're doing, make sure you guys for sure know what's going on. Guys, 3 different experiments. You guys proposed these 3 independent variables. How many independent variables do you guys have at one time? One. And the other 2 you're going to control, right? So maybe this could be independent variable and then these 2 are controlled. That's one experiment. Then the next lab table, next experiment, you just change what your independent variable is and leave the other 2 variables controlled. And then the third one. All right. Okay, go ahead, gather your data today and walk around, help you guys out.
Okay.